Lecture 24. T-Junction and resistive power dividers. Have a look at a simple lossless T-junction network as shown in the figure. So here, a T-junction network, hence the name T, is like T. Okay, so you have three ports, port 1, port 2, and port 3. With all the voltages, respective voltages, incident voltage, and also reflected voltage. So there are two basic constraints we need to incorporate into this power splitter. So the first one, the feed line, should be matched. So it should be matched over here between port 1 to port 2 and port 2 to port 3. Next, the input time average power P in should be divided between ports 2 and port 3 in a desired ratio, meaning that the power that is incoming from port 1, which is P in over here, the ratio between the power that goes into port 2 and port 3 should be divided into some ratio. So in the text, this ratio is defined as x to y. So the first one is when you have x over x plus y times 100% of the incident power is delivered to one output port. Or you can have y over x plus y times 100% of the incident power delivered to the other. For example, if you have a 1-to-1 ratio, meaning that 50% of the incident time average power is delivered to each output port, meaning that port 1 will have 50%, port 2 will have 50% and port 3 will have 50%. But if you have a ratio of 2-to-1, meaning that 67% of the incident time average power is delivered to one output port, say output 2, and the remaining to the other port. So 33% will go to port 3. Referring to the circuit, in order to enforce the first constraint on the power splitter, so we require that Y in should be equal to 1 over Z0. So 1 over Z0 is the addition of 1 over Z1 plus 1 over Z2. So in order to divide the incident power between the two output ports, what you have to do is just adjust the characteristic impedance of the two transmission line. Since we assume that port 1 is matched, so the input time average power would simply be P in is equal to 1 over 2 times with magnitude of V0 squared over Z0, where V0 is the total voltage at the junction. Now you are able to find P1 over P in is equal to Z0 over Z1, and P2 over P in would be equal to Z0 over Z2. So having all this, you have ensured that the feed line is matched. So now you are able to compute the required characteristic impedance, which is Z1 and Z2, by applying the formula here. So Z1 would be equal to Z0 over P1 over P in, and Z2 would be equal to Z0 over P2 over P in. Now, there are two important points that you have to consider when you want to design the T-junction power splitter. So the first one is the junction effects. So junction effect is when you have an accumulation of excess charge at the junction. Okay, take the microstrip junction in the figure over here. So here at the junction you have an accumulation of excess charge. So this charge attracts oppositely signed charge on the ground plane. So what you have to do is you have to model this effect as a lump capacitor which connects to the ground, as shown in figure 7.6. Now, next one, you have to consider the characteristic impedance of the output lines. It is not too practical to have Z1 and Z2 characteristic impedance in the system. So we generally like to work with just one system impedance, which is Z0. So one approach to resolve this issue is by adding the impedance matching circuit to the end of the port 2 and port 3. So over here at port 2 and port 3, in order to make it match at the junction here, what you have to do is have the quarter wave transformer, QWT. So this QWT is actually the impedance matching circuit. So that's why you have QWT1 at port 2 and QWT2 at port 3. So this quarter wave transformer act to transform Z0 to Z in 1 and Z0 to Z in 2 in order to make it match. So, however, there is a disadvantage of using a quarter wave transformer where it will make the power splitter narrow banded. Next, lecture 25, the Wilkinson power divider. Okay, consider the 3-port network in the figure. So this is a power divider. So for Wilkinson power divider, it is 1-to-1. Okay, so 1-to-1 power divider. So here you have port 1, port 2, and port 3. Lambda over 4 here would be your quarter wave transformer. Okay, hence the name lambda over 4, quarter wave. So this is a popular power divider because it is easy to construct and has some extremely useful properties. First, it is matched at all ports. Okay. Number 2, there is a large isolation between output ports. Number 3, it is reciprocal. And number 4, it is lossless when output ports are matched. So there are two types or two configurations of the Wilkinson power divider. The first one is the symmetric and the second one is anti-symmetric. So we will now show that for a 1-to-1 Wilkinson power divider, the Z0Q is equal to the square root 2 times Z0 and R is equal to 2 times Z0. So to simplify matters, we will use first normalize all the impedances to Z0 and number 2, not draw the written line for the transmission line, meaning that your transmission line with characteristic impedance to Z0 will be delineated as this. There are no written line, meaning that there are no reflection. So here, hence the Wilkinson power divider shown in the first figure above. So this is the first figure that we have for the Wilkinson power divider. After applying the two characteristics before, so we will have this figure. It has been simplified, where you have normalized your impedance to only Z0. So here you have Z0, Z0Q and Z0Q. And then you not draw the written line for the transmission line, meaning that there are no reflections.